to explain that the Atlas detector is built in many, many layers doing different jobs. That was what I was beginning to explain to the other group. So when they come down from the movie, I can explain to all of you together. So here are the people working on each of those, monitoring the performance of it, making sure that every part of the detector is working perfectly, so that we can rely on the quality of the data. So they're in their different consoles, whether they're identifying the particles, whether they're measuring the energy and so on. I should have explained, as I did to the other group, when the protons, or perhaps lead nuclei, collide together, most of the time they're just glancing collisions, rather boring collisions, but occasionally we get a good head-on collision, and perhaps we will make one of these exciting new particles that hasn't been seen before. You all know the formula E equals mc squared. The more kinetic energy we have in our collisions, the higher the mass of the particles we can make. But they will all be extremely short-lived. We might make Higgs bosons, nobody's seen those yet. We might make particles of dark matter. You know that there's not enough mass, visible mass in the galaxy to hold the stars in. The stars ought to be shooting off at a tangent. There has to be a lot more mass in the galaxy than we can see, about 6 or 7 times more than there is in stars, and we call that dark matter. Now, if that's made of particles, we should be able to create those particles here and study their properties. There's lots of different names for them, but the one I like is weakly interacting massive particles, or WIMPs. So we may be able to create WIMPs. We may even be able to make mini black holes. That's most unlikely, and they will be really mini black holes. Remember, individual protons only have the energy of a mosquito when they collide, but of course crammed into a very tiny space. So all of these particles will break up almost immediately. We won't see the Higgs bosons, the WIMPs and so on. What we will see is the particles that come out from them, so we have to measure those and identify those. And the bunches pass through each other 40 million times a second. So these people are looking after the detectors, making sure everything's working perfectly. And you'll notice that most of them are young people. They're PhD students from the different universities and institutions that collaborate on this detector. There are 1 or 2 older people like myself, but most of them are PhD students. So when I bring school groups round, which I do quite often, I point out to them that it's going to be too late for me to discover the Higgs boson. These collisions making Higgs bosons will be very rare, so it'll take a number of years to build up the required statistics to convince ourselves and the rest of the world that it really is there. Or convince ourselves that it isn't there, which would be even more interesting. It means we have to rethink our physics. So I shall be back at home in my armchair reading about the Higgs boson in the newspapers. But these young people, they can get their maths and physics school-leaving exams, they can do a bachelor's in physics, and then join a particle physics group to do a PhD and come here to CERN and help us discover the Higgs boson. It's not too late for them by any means. There's one other group I should mention, that's this group in the front on the right here. They bring together the data from the different subdetectors and send it across to the CERN Computer Center. And we call that data acquisition. And DAQ, or DAC, and that's why we have the ducks, little plastic ducks on top of the console there.
You brought it back to my level, thank you.
Okay, now the black screen with the blue band across tells you what's actually going on in the collider, in the LHC, to give them the colliding particles to do their experiments. And at the moment, as you can see, it says proton physics. That means we're colliding these light particles, protons. In about 6 weeks' time, we will switch over to colliding the heavy lead nuclei, but it's protons at the moment. And they're doing an injection of the probe beam. Although each individual proton, when they collide, only has the energy of a mosquito in flight, each bunch of protons has 100 billion protons in it. And when we're working at full intensity, we will have up to 3,000 bunches going round. So the total energy stored in the beam coasting round is the same as an express train. And it's very important that it goes centrally down the vacuum tube. Remember, most of the time they're in 2 separate vacuum tubes so that they don't collide with gas atoms, and they're only bent to collide together at each of the 4 experiments, each of the 4 detectors. So to make sure that all the magnets are at their correct settings, all the collimators are adjusted correctly to let the beam go right the way round. Instead of putting in an express train's worth, they just put in a probe beam, one bunch, make sure it coasts round, and then they can inject all the others later. So in about, I don't know, half an hour, three-quarters of an hour, that will switch to beam setup. And then finally, they will squeeze the beams down so that you get higher collisions. I can't remember whether I said to all of you or just to the other group. What we want is to have the tightest possible beams. Did I say that? No, okay. You can imagine if you have a group of people crossing a field, they're not going to bump into each other. But if you put them into a narrow tunnel, they'll bump into each other all the time. And since we want as many collisions as possible from our protons, we focus them down to a fine needle-like beam. So we want these two needle-like bunches to pass through each other. And so that's what they'll do. They'll squeeze them down and then finally adjust them so that they do actually meet each other in the center of the detector. We operate the machine, generally we fill it about once a day, because although the beams start off nice and narrow like that, so we get lots of collisions, and although only a very few protons collide together each time they pass through 40 million times a second, and on average about 20 proton-proton collisions take place. But remember, the protons are all positively charged, so as they go through each other, they repel each other, and that blows the beam up, so that the number of collisions goes down. And after about a day, it's worth dumping those beams, switching on a magnet, and sending that energy of an express train into a 100-meter long block of water-cooled iron, and re-inject new, fresh beams with lots of more collisions in. So that's what happened. They were running from about 6 o'clock last night, all through the night, with collisions. Then they dumped those beams and they're refilling at the moment. But as I said, just to start with, they have this probe beam. Of course, when the LHC is running, it does run round the clock, and so the people here work in 8-hour shifts. So this is Atlas, and as you'll see, Atlas is only about a 5-minute walk from the restaurant at CERN. My experiment, CMS, is the far side of the ring, so it's about a 35-minute drive back to CERN. So what we do is, instead of having a big control room like this, we have a small a skeleton group of people actually working at the surface above the experiment, just in case something goes wrong and they have to go down and press a button to reboot a computer or something like that. But by the time you've taken the data up 100 meters, you may as well take it 10 or 12 kilometers to the main CERN site. So we have a room like this on the main CERN site, where our people are checking on the quality of the data and making sure that everything is working perfectly. We also have a lot of Americans working on the experiment. The total number of people is 2,500, of which nearly 1,000 are Americans. And of course, they don't want to come flying into Geneva to do their shifts and go back home all the time. So we actually have a control room like this at Fermilab near Chicago. So the advantage of that is that when it's midnight in Geneva, it's only 5 p.m. in Chicago. So we can go to bed and they can take over monitoring the experiment to make sure that everything's working perfectly. And when it's bedtime in Chicago, we have a third control room in Beijing, in the People's Republic of China. So they can look after the experiment until it's time for us to wake up and go to work. So as they say, the sun never sets on CMS. But as far as I know, and I've asked some of the Atlas colleagues, this is their only control room. Of course, you can spy on the experiment, you can check on what's happening from your own university as well, and that's done in both CMS and Atlas. But the majority of the checking is done from these control rooms. Again, I've forgotten what I've just said and what I've said to you. Did I mention that they're mostly young PhD students here? Did I mention about the chance to? Okay, good. What I do say to those people is that, of course, if they've made a mistake and they choose not to study physics at university, it's not too late, because once we've found the Higgs boson, there'll still be lots of experiments to do to measure its properties in detail. We will probably continue to run the experiments on the Large Hadron Collider for 15 or 20 years. And there are already plans to build the next generation of collider. Of course, we haven't asked for the funding yet, But, so we need to know the mass of the Higgs boson, we need to finish the design, we need to choose where to build it. CERN would like to be the host, Fermilab would like to be the host, the Japanese would like to be the host. So there'll be some international squabbling for a year or so to choose where to build it. Then we've got to ask for the money for it. So that'll be 25 or 30 years down the line. So these young school children, I tell them if they've made a mistake and they're going to study engineering or accountancy or something, don't worry, their children can go to school, get their exam results in maths and physics, do a bachelor's in physics, and then do a PhD on one of these, on this even bigger collider. So there's plenty of physics for generations to come.
Are you familiar with Sudbury?
In Ontario, yes, sure, yes, yes.
Okay, I'll say it's an accelerator, is that correct?
No, because it uses, well, it uses particles, not protons, it uses neutrinos generated at Fermilab. They go through the rock, some, I don't know, 400 miles, is it, from Chicago to Sudbury?
That would be conservative, yeah, probably 400 to 500 miles.
Okay,
Anyway, it's right in
yeah, and then they're detected there. So
But isn't it circular, some kind of a circular?
in Chicago, yes. But then they point the particles. Your Sudbury observatory is a big hole in the ground.